All right, electrolytic versus voltaic cells. In section 21.1, you learned how a spontaneous chemical reaction can be used to generate a flow of electrons, an electric current. In this section, you will learn how an electric current can be used to make a non-spontaneous redox reaction go forward. The process in which electrical energy is used to bring about such a chemical change is called electrolysis. Although you may not have realized it, you are already familiar with some results of electrolysis. Silver-plated dishes and utensils, gold-plated jewelry, and chrome-plated automobile parts are a few examples. The apparatus in which electrolysis is carried out is an electrolytic cell. An electrolytic cell is an electrochemical cell used to cause a chemical change through the application of electrical energy. An electrolytic cell uses electrical energy, direct current, to make a non-spontaneous redox reaction proceed to completion. The vast array of electrolytic cells shown in figure 21.11 are used for the commercial production of chlorine and sodium hydroxide from brine, a concentrated aqueous solution of sodium chloride. That's brine, is a concentrated aqueous solution of sodium chloride. Now, in the next figure, 2111, as mentioned, to produce chlorine and sodium hydroxide in electrolytic cells, electricity is passed through brine, a sodium chloride solution. The products have many uses, such as disinfecting swimming pools, cleaning drains, manufacturing soap, and producing paper pulp. So the cell A on the left is a voltaic cell and B is an electrolytic cell. A voltaic cell uses a chemical change to produce an electric current, and in an electrolytic cell, it uses an electric current to produce a chemical change. 21.12, figure 21.12. Electrochemical cells can be classified as voltaic or electrolytic. A. In a voltaic cell, energy is released from a spontaneous redox reaction. The system, or the cell, does work on the surroundings, a light bulb. B, in an electrolytic cell, energy is absorbed to drive a non-spontaneous reaction. The surroundings, battery or power supply, do work on the system or the cell. Now, in summary, comparing and contrasting, how are voltaic and electrolytic cells similar and how are they different? So remember, the voltaic cell is a spontaneous chemical reaction that produces an electric current, and an electrolytic cell is a non-spontaneous chemical reaction that is driven by an electric current. So they're very different, yet in some ways similar. In both voltaic and electrolytic cells, electrons flow from the anode to the cathode in the external circuit. As shown in figure 2112 that we just saw, for both types of cells, the electrode at which reduction occurs is the cathode. The electrode at which oxidation occurs is the anode. The key difference between voltaic and electrolytic cells is that in a voltaic cell, The flow of electrons is the result of a spontaneous redox reaction, whereas in an electrolytic cell, electrons are pushed by an outside power source such as a battery. The redox process in the voltaic cell is spontaneous. In an electrolytic cell, the redox process is not spontaneous. Electrolytic and voltaic cells also differ in the assignment of charge to the electrodes. This is important. In an electrolytic cell, the cathode is considered to be negative electrode. This is because it is connected to the negative electrode of the battery. Remember that in a voltaic cell, the anode is the negative electrode and the cathode is the positive electrode. The anode in the electrolytic cell is considered to be the positive electrode because it is connected to the positive electrode of the battery. It is important to remember these conventions about the two kinds of cells. Here is an electrolytic cell where it is the electrolysis of water using a salt that is not easily oxidized, such as sodium nitrate or potassium nitrate or sulfuric acid. Figure 21.13, when an electric current is passed through water, the water decomposes into oxygen and hydrogen gas, interpreting photos. Which electrode is in the photograph is the cathode and which is the anode? Very important question to answer. So here we have oxygen. You can see that it's a smaller volume, and hydrogen has literally twice the volume. And the oxygen is being produced at one of the electrodes, and hydrogen is being produced at the other electrode. So this is a non-spontaneous reaction. Now, the reverse is spontaneous. Hydrogen plus oxygen yields water. Very spontaneous. But this is the opposite. Water does not spontaneously change to oxygen and hydrogen. That would be a little crazy. Can you imagine? You're drinking a glass of water and boom, it becomes hydrogen and oxygen. So this is a non-spontaneous reaction, and it requires an electric current. And that's the nature of an electrolytic cell. Electrolysis of water. When a current is applied to two electrodes immersed in pure water, nothing happens. There is no current flow and no electrolysis. However, when an electrolyte such as sulfuric acid or potassium nitrate in low concentrations is added to the pure water, the solution conducts electricity and electrolysis occurs. This process is illustrated in figure 21.13. The products of the electrolysis of water are hydrogen gas and oxygen gas. Let's look at this picture again, and you can see that the oxygen is on the left and the hydrogen is on the right, and the hydrogen is twice the amount relative to the oxygen. That's critical in understanding the equation for the electrolysis of water. Remember your gas laws. Gases are all the same. If I have 1 mole of a substance, 1 mole of any gas at STP is 22.4 liters. 1 mole of chlorine gas, 1 mole of oxygen gas, 1 mole of hydrogen gas, 1 mole of any gas at STP is 22.4 liters. Now let's say I have the same amount. Let's say I have 0.1 moles of hydrogen, 0.1 moles of oxygen. Well, it's going to be the same volume. If I have twice the volume, I have twice the moles. So if I have 0.1 moles of oxygen and 0.2 moles of hydrogen, I'll have twice the volume for the oxygen. That's very important in remembering when it comes to this next slide relative to the electrolysis of water. So the water, 2H2O liquid plus 2 electrons, is going to yield hydrogen. And we know that's reduction because the H in water is +1 and the oxygen is -2. So it's going to go from +1 to 0. So it's going to become less positive. That's reduction. And that's going to be at the cathode. And then the oxidation is going to be the water, which has oxygen is -2, and that's going to go to oxygen, which is 0. So that's going to become more positive, and that's going to be oxidation. And that's going to happen at the anode. The region around the cathode turns basic due to the production of OH ions. OH ions. So I'm going to rip that hydrogen from the water, and I'm going to be left with OH. Think of water as HOH. HOH. If I take the left-hand hydrogen off, I'm left with OH, and that's what happens. So I'm left with an OH, okay, and it's going to become basic around the cathode. The region around the anode turns acidic due to an increase in the H+. So think of it as H2O now around the anode. So I'm going to take off the oxygen. I'm left with 2 H+, which is acidic. Okay, so around the anode, I'm going to take the oxygen. I'm going to have left over H+, and that's going to be acidic. The overall cell reaction is obtained by adding the half reactions after doubling the first one to balance the electrons, the reduction plus the oxidation, and the overall reaction is 6H2O yields 2H2 plus O2. But remember that the ions produced tend to recombine to form water. Okay, remember those acidic ions and basic ions? They're going to recombine to form water, and you're left with, at the bottom, you're left with 2H2O. Electrolysis yields 2H2 plus O2. That's the important equation. So the three important equations are the reduction equation, that's the first one, as you're reading from top down. The next one is the oxidation reaction, and then the other one that's important is at the bottom, the 2H2O plus yields 2H2 plus O2. Now, notice 2H2 plus O2. So 2 moles of hydrogen are produced for 1 mole of oxygen. That's where you get 2 times the volume of the hydrogen compared to 1 part of the oxygen. So you get twice the amount of hydrogen than you do oxygen. So here is the electrolysis of brine. Now, the reason you don't use sodium chloride in the electrolysis of water to produce oxygen and hydrogen is because if you use sodium chloride, the oxidation of the chlorine would outcompete the oxidation of the oxygen at the anode, and you would produce chlorine gas instead of oxygen gas. And it's kind of stinky and not good for you. So you would need to use a more stable substance, such as sodium nitrate or sulfuric acid or potassium nitrate, where the anion is not easily oxidized. And you can see here the chlorine is oxidized at the anode. So the electrolysis of brine is actually pretty interesting. You take a concentrated solution of sodium chloride, you run an electric charge through it, and at the anode you're going to produce the chlorine, that's oxidation of the chloride ion, and at the cathode you're going to produce hydrogen. Now, notice that you're going to produce, like, remember that HOH, you get rid of the H and you're left with OH. So you're left with sodium is the spectator ion, and you're left with sodium hydroxide. So you're actually producing three things. You're producing chlorine gas, which has a zillion industrial application. You're producing hydrogen gas, which has a zillion, maybe 2 zillion industrial applications, and you're producing sodium hydroxide, which has 10 zillion industrial applications. And figure 2114, the electrolytic cell used for the electrolysis of brine, which substances are produced by oxidation and which are produced by reduction. So you can clearly see that the chlorine is being oxidized and the hydrogen is being reduced. So the oxidation is occurring at the anode, and that's going to be chlorine, and then the hydrogen is being produced at the cathode, and that's reduction. Electrolysis of brine. If the electrolyte in an aqueous solution is more easily oxidized or reduced than water, then the products of electrolysis will be substances other than hydrogen and oxygen. An example is the electrolysis of brine, a concentrated aqueous solution of sodium chloride which simultaneously produces chlorine gas, hydrogen gas, and sodium hydroxide. The electrolytic cell for this process is shown in figure 21.14. And there it is again. We've actually been through this, and I think we did a pretty good job of it. But just ponder that weak and weary and see if it can make sense. Make sure you know the anode reaction, the cathode reaction. You're producing hydroxide ion at the cathode, and the sodium ion is the spectator ion. During electrolysis of brine, chlorine ions are oxidized to produce chlorine gas at the anode. Water is reduced to produce hydrogen gas at the cathode. Sodium ions are not reduced to sodium metal in the process because water molecules are more easily reduced than sodium ions. The reduction of water produces hydroxide ions as well as hydrogen gas. Thus, the electrolyte in solution becomes sodium hydroxide. The half reactions are, therefore, oxidation is the chlorine ions becoming chlorine gas at the anode, and water becoming hydrogen at the cathode. That's the reduction. The overall ionic reaction is the sum of the two half reactions. 2 chloride ions plus 2 waters will yield 1 chlorine gas and 1 hydrogen gas and 2 hydroxides. The spectator ion sodium plus 1 can be included in the equation as part of sodium chloride and of sodium hydroxide to show the formation of the sodium hydroxide during the electrolytic process. 2 sodium chloride ion, formula units plus 2 water molecules yields 1 chlorine gas one hydrogen gas, and 2 sodium hydroxide formula units. Notice I say formula unit. A formula unit is an ionic compound, where a molecule, such as water, is a molecule. So I have 2 formula units of sodium chloride plus 2 molecules of water yields 1 molecule of chlorine gas, 1 molecule of hydrogen gas, and 2 formula units of sodium hydroxide. Or, putting it another way, 2 moles of sodium chloride plus 2 moles of water yields 1 mole of chlorine gas plus 1 mole of hydrogen gas plus 2 moles of sodium hydroxide. When the sodium hydroxide solution is about 10% mass to volume, it is removed from the cell and processed further. Using electrolysis in metal processing. Electrolysis has many important applications in the field of metallurgy. Electrolytic cells are commonly used in the plating, purifying, and refining of metals. Many of the shiny, metallic objects you see every day, such as chrome-plated fixtures or nickel-plated coins, were manufactured with the help of electrolytic processes, electroplating and electro forming. Electroplating is the deposition of a thin layer of a metal on an object in an electrolytic cell. An object may be electroplated to protect the surface of the base metal from corrosion or to make it more attractive. An object that is to be silver plated is made the cathode in the electrolytic cell. Let me say that again. An object that is to be silver plated is made the cathode in an electrolytic cell. The anode is the metallic silver that is to be deposited. And the electrolyte is a weak solution of silver salts, such as silver cyanide. When a direct current is applied, silver ions move from the anode to the object to be plated. So the reduction would be silver plus 1, silver ion, plus an electron yields solid silver at the cathode. The net result is that silver transfers from the silver electrode to the object being plated. Figure 21.15 shows a silver-plated T-set. Many factors contribute to the quality of the metal coating that forms. In the plating solution, the concentration of the cations to be reduced must be carefully controlled. The solution must also contain compounds to control the acidity and to increase the conductivity. Other compounds may be used to make the metal coating brighter or smoother. Electro forming is a process in which an object is reproduced by making a metal mold of it at the cathode of the cell. For example, a phonograph record can be coated with metal so it will conduct a current. It is then electroplated with a thick coating of metal. This coating can be stripped off and used as a mold to produce copies of the record. That's very old technology in the production of albums, record albums. Electrowinning is another process called electrowinning. impure metals can be purified in electrolytic cells. The cation of molten salts or aqueous solutions are reduced at the cathode to give very pure metals. A common use of electrowinning is the extraction of aluminum from its ore, bauxite. Bauxite is impure alumina, Al2O3, in a method known as the Hall-Héroult process. Purified alumina is dissolved in molten cryolite, that's Na3AlF6, and heated above 1000 degrees Celsius in a carbon-lined tank. The carbon lining connected to a direct current serves as the cathode. The anode consists of carbon rods dipped into the tank. At the cathode, Al+3 ions are reduced, forming molten aluminum. At the anode, carbon is oxidized, forming carbon dioxide gas. Now, before this process of electrowinning for the production of purified aluminum was developed, aluminum was extremely expensive. You didn't have aluminum foil around the kitchen like you have now. You didn't have everything made of aluminum, lightweight, easily to transport, etc. Aluminum was extremely, 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 extremely expensive. So you are a recipient of all the electrochemistry research that went into the production, the inexpensive production of aluminum metal. Electro refining is the process of electro refining. A piece of impure metal is made the anode of the cell. It is oxidized to the cation and then reduced to the pure metal at the cathode. This technique is used to obtain ultra-pure silver, lead, and copper. Other electrolytic processes are centered on the anode rather than the cathode. In electro polishing, for example, the surface of an object at the anode is dissolved selectively to give it a high polish. In electro machining, a piece of metal at the anode is partially dissolved until the remaining portion is an exact copy of the object at the cathode.